Okay, so hopefully this presentation will answer some of the questions from the usability perspective and about the process for going through uh, the model reduction process and the porting of the model over into a real-time environment and some of the general concerns that people need to handle there. Uh, so I've got just really 6 topics to cover here. First, just a high level, and we will go through that pretty quickly because it covers some of the things that we've already talked about. And then what that model reduction process looks like. How do you tell when you've gone fast enough? A few things about integrating that into the ecosystem of tools that you're going to connect it to. Some of the challenges that you might hit along the way, and then a little bit about what else we're working on with different folks right now. Okay, so you know, one of the great selling points of using atoms for real time is that you can do whatever you want. The model isn't a fixed black box with regards to the model content and what needs to be there or not be there, and you can decide what input and output channels you might want. Unfortunately, that's also the bad news, right? I mean, uh, since you can do whatever you want, it puts the responsibility back on the users to craft some sort of a working real-time environment. And that does take a little bit of an extra work and a little bit of extra development of capability, and you have to feel your way through it a little bit. So MSC is really providing a tool set together with our partners in this space to enable this. And then the user needs to tailor that solution for their application, for whatever hardware and software they want to attach it to, and then the kind of compute performance and sampling rate that they need for that application in order to be successful. And that varies by application, budget, time, all of those things. Uh, so getting into this model reduction process, I'm going to start with the easy slide here, which is the big hitters. First thing is decide who you can cut out of your life. This model often on the vehicle side of things is focused on satisfying a lot of different stakeholders, but the real-time model does not have the same stakeholders. And so there might be model content that was extra in the first place, or that was put in for the durability group or put in for the ride group. And maybe those guys aren't going to be involved in the real-time process, and you can cut out some of that content uh, just based on the stakeholders involved. And then also sometimes, depending on who put together the model and how sophisticated the modeling process is, sometimes there's extra stuff in the model that's slowing it down that you don't need regardless of the stakeholders. So a little bit of attention to whether you've got extra parts or kind of sloppy modeling practices in the model that could speed it up out of the gate also is worth looking at. Okay, step 3, you've got some obvious candidates that you can't necessarily keep up with in real time. So I should back up and talk about the overall goal here is typically what we've been seeing is we're talking about getting this model down to somewhere in the 120 to 160 degrees of freedom for applications in the 500 to 1000 hertz range. So when you look at something like a beam-based anti-roll bar or a beam-based leaf spring, those may contribute hundreds of degrees of freedom on their own. So they've got to go. You can take them one way or another uh, down to a simplified method. Adam's car has simplified some tools to get their beam-based anti-roll bar reduced automatically. As we discussed with Tony's presentation, we've been taking those models down to 5-link representations as a some services work to help forward out with that. Um, Generally, we need to take the flexible parts out. There may be some capability to do that. We'll talk about that a little bit more later. And then there's other things that we've put in kind of in parallel, like high performance tire options and things that allow you to get faster performance without sacrificing too much simulation time. Okay, so now we get into the harder part. We go from our nice, clean, simple, idealized flowchart to more of a real flowchart here. Uh, so now we've got to start chipping away at things. Sometimes you have less critical subsystems that can be cleaned up or simplified down. So depending on your application, maybe you're focused on the steering, but you can reduce the powertrain fidelity. Maybe you can reduce the driveline fidelity, but you need the engine power. Maybe like in Tony's case, we so far haven't really been concerned about the steering fidelity, so we can reduce some of the content there. And some of our standard shared templates may help in this way, partly because those are what we test with real time internally, and we have more familiarity with helping out on those kinds of things. Um, Obviously, compliance and degrees of freedom are pretty tightly connected. Uh, a control arm with bushings on both ends has 6 degrees of freedom. A control arm with bushings on one end has 3, right? So if you're trying to take these out, take your degrees of freedom down a little bit at a time, then um, you may need to take out some bushings that are less critical for your application, or things like you may have compliance in a drive shaft, compliance in half shafts, things like that that you can reduce for your application. And then we get into things like splines, diffs, GSEs in the model. Depending on how much you've got in there, some of those things may need to be scrubbed down a little bit. Um, so you generally get into this a little bit of an iterative process where you do some cleanup, you check your model speed, see how your speed is doing. If you're not where you need to be, then you got to take some more out. At this stage, when you're going through this, uh, say on your own, on a desktop kind of environment, then you typically want to, I would recommend taking that down a little bit further than you might need to go to start with, so that you've got something that's a little more rock solid. You're sure it's going to meet real-time specs, and you can do the hardware integration with that kind of a model, and then come back around if you've got a little bit of margin, you can come back around and add some compliance, add some extra fidelity back into that model. There's a real temptation to be greedy. After all, you built that model in the first place to be as representative as possible, and now you're forced with making hard decisions to make it less accurate in some way or another. And so you always end up pushing back up against that limit of real time to see what you can get away with. At the end of the day, once you've got something that's fast enough, we've got the ability to make that FMU parametric. So you need to pick which kind of parameters you might want to expose for your real-time application, expose those within the interface, export an FMU to use on the concurrent side. As you're trying to test how fast you're going, um, typically you want to start by saying we're going to define an event that is kind of typical to what you're going to see in the real-time environment. So even though you're going to get maybe a closed loop brake inputs or driveline inputs, let's make those open loop and define them, predefine them to give my model a test, and then start looking at how fast that's going. Usually to be representative, you need to turn on that fixed step integrator. That's what real-time is using. We've got this H ratio parameter that allows you to take more or less steps in between your communication intervals. I set the threads up there to be something kind of comparable to what you'll see on the real-time side. So at least usually you can get at least 4. It might be 8 or more. And then you want to make sure you're turning off your output on the Adams side, so you're testing like you will in the real-time environment. Typically, your desktops are going to be slower than your actual hardware in the loop machine, and that's typically 15 to 25% different. So when you're testing on your own, you can be, say, 10% slower than real time on your machine and still 5 to 10% faster than real time once you get onto the real time box. And once you actually start going back and forth between your model and the real time box, then you'll know a real speed ratio that you can work with on that. And you don't really want to set that up so that your model is running at 98% real time, because there's always a couple little things that come in, a couple little blips now and then that slow you down a bit, and you don't want to run over in that case. However, you also can keep in mind what happens when you go over. In some HIL scenarios, they really track the overruns carefully, and if you have too many, the hardware shuts down, the cell shuts down, everything stops. That's a problem. But other software in the loop environments or other situations are not so rigorous, and a couple little glitches here and there are acceptable. Okay, once you have a model and it's fast enough and you're ready to plug it in, uh, you're going to take your FMU and pop it in to work with a concurrent machine, a DSpace machine. You may be connecting it to VTD, maybe maybe all three of these, maybe two of them. It's kind of a wild ride out there. And then that's going to be interfacing with the hardware, interfacing with software. So there's a lot of parties here that may need to work together. All of the tools are compatible, so there's no programming or major development work that needs to happen, but you do need to expect that probably everybody involved is going to have to be in the same room at the same time talking to each other in order to iron out the details, so that you really make sure that everybody's communicating and that the signals are being exchanged at the proper speed and as everybody expects. So every time you put all these things together, you get kind of a unique combination of tools, signals, hardwares. The application is always a little different. The conventions at different companies are a little bit different. And after you try to plug everything in, there's a good chance that everybody's going to need to go home and do a little bit of homework to adjust, what is the exact implementation that Concurrent is using? What is the expectations of the hardware? What kind of actuators do you have there? What kind of filters do you have there? There's a little bit of back and forth that needs to happen on everybody's front to make that work. And then, there are some hurdles that are likely to come up here. One is, right, we do have a big ecosystem of tools like we were just talking about on that last slide. And all of those tools have different requirements, different expectations. Uh, Quite often, we're pulling the Adams model out and or putting the Adams model in place of another model, right? You might be taking a Carson model out of there, or some other reduced degree of freedom model out and putting in an Adams model, and you want to make that as uh, you don't want to add any extra disruption there. You want to make that as simple as possible, which means you may have to share signals or reuse the same signals that the other tools were using, and that may mean you need to convert units or adjust to make that work. And if it doesn't work, when it doesn't work, then you want to make sure that everybody's kind of got a team mentality, and you're not pointing fingers uh, uh, to lay the blame at one tool or the other. Everybody's going to be in that together, and if you kind of set that expectation to begin with, it's helpful. This is still Adams. Adams Solver doesn't like discontinuities, and that's not any different in real time than it is with other models. So sometimes we've found that we need to add transfer functions or other kinds of smoothing considerations to the signals so that Adams will take them and not go unstable or cause a simulation failure. And of course, just like, always, you have to keep track of your signs and your units and things. And, like you saw Tony's presentation, they do calibration runs to say, here's a set of predefined inputs. If we give those predefined inputs, we expect these outputs. Do some calibration of that model to make sure that when you put in a known input, you get very close to a known output. And then the other hurdle here is that the people that are using this system are not CAE engineers. They're not Adams folks. They don't understand markers and step functions and impact functions and V forces and S forces, and they don't want to hear about those things. They just want this thing to work like a toaster. You plug it in and it works. And so you need to have that level of expectation of yourself and of your model in order to be successful in the process, or else they're going to be knocking on your door every other minute. They're going to get pretty upset pretty quickly if it's not a robust model, or if the parameters that you're feeding it don't work reliably. We are doing a couple of different things. We've seen some of this information from Ian at the beginning and things. We're always trying to improve our base solver efficiency, so that that's a rising tide that lifts all boats, including real time. The faster we go with our solver, the more degrees of freedom you can put in the model, the less compromise you have to make. We're looking into some investigations that will allow us to get a clean assessment of what kind of flexibility you can include in the model, what you can get away with there. For sure, if you have a simple enough flex body and not too much attached to it, we can do it with real time. But for real scenarios, flexible subframes, flexible chassis, what can we include and what do we have to throw out to make it work? We want to look into that, and we have some plans on that. We're always looking at improving our capabilities with concurrent and DSpace. We continue to work on different methods for integrating our driver controller into this process. Sometimes, depending on who's in the loop and who's not in the loop, that our driver may still need to participate. So we've got some activities with that. And then there's a number of different numerical up and down sampling kind of options that we're working through with the solver to allow a little more flexibility there in some circumstances. All right, so that's all my content.